Welcome back. With this video, we're starting our section on making code more bug resistant. In this section, we're going to focus on two methodologies to making our programs less prone to failure. The first of these is by running a static analysis program on our code, which checks that our assumptions about what kind of data we're handling are always correct, helping us prevent a whole category of errors where we expect one kind of data and receive another. The second is by running an automated test suite that we've written for our code, confirming that in each of our test cases the code actually does what we expected. The tests in our test suite tend to accumulate over time, because keeping them around and running them each time we run the test suite means that our progress on the program never goes backwards. If we do something that would undo a previous bug fix, the tests for that fix will catch it. In the end, we'll apply what we've learned to our ORE code and find a few bugs while we're at it. Let's start with a video using type annotations to make our code more bug resistant. In this video, we're going to learn Python annotation syntax and how to use it to specify our expectations about the data types we expect our variables to contain. Then we'll expand into the features of the typing module, which provides us with an assortment of ways to talk about the types more generically. For example, using the typing module, we can specify that a variable needs to contain a sequence, which might be a list or a tuple or something else, instead of requiring it to be a list specifically. We'll learn how to use the MyPy tool to run a static analysis of those type annotations, which will tell us if violating our assumptions is ever possible, and where those violations could occur. Incorrect assumptions are a major source of bugs, so this can be a big help. Here we have a little program which implements very simple map and filter functions, along with a predicate function called even and an operation function called add. A predicate function is just a function that tests for some condition and returns true or false. None of these are particularly useful, since each of them only encapsulates a single Python expression, but they'll help us illustrate how to use type annotations. At the end of the program, we set out something very similar to the pipes we used in ReactiveX, which isn't surprising since this is a functional programming structure, and ReactiveX was inspired by functional programming. In this case, we create a list of tuples, map the add function across that list to create a list of single values resulting from adding the two items to each other, and then filter out the values that aren't even before printing the overall result. We do this twice, and the only difference between the first and second times is the content of one of the tuples in the input list. So there's nothing actually wrong with our code as long as what we feed in is a list of pairs of numbers. It does what it's supposed to do. But if we feed in something else, things can go wrong, and there's nothing to warn us of that until we run it and get a type error about string formatting. That error is particularly confusing since we're not using string formatting anywhere, at least not on purpose. Most of the time the error we receive won't be quite that bad, but we won't know anything's wrong until we get the exception trace back. And then we'll have to work backwards through the code to figure out why it's happening and where the best place to fix it is. Even that's not so bad. Python has always been easy to debug. However, we only see an exception at all if we think to test the particular kind of faulty input that causes it. And if it's not us who receives the exception, well, that means it's somebody else. A client, perhaps, or a coworker. Not only does that make debugging rather more difficult, it makes a bad impression. Here we have the same program, except with our assumptions written into the code so that they can be checked. First off, we import what we need from the typing module, which is built into Python. In this case, we want to be able to describe tuples of a specific length and containing specific types of data, iterables that produce a specific kind of data when we iterate over them, and callables with specific data types for their parameters and return values. After that, we declare that a pair is a two-tuple of integers. That just means we can use the word pair when we would have otherwise used tuple, square bracket, int, comma, int, square bracket, which should be easier to write and read. The use of square brackets to identify type parameters is common throughout Python's type-checking landscape. It keeps type-checking information visually distinctive and provides convenient semantics. Now, our add function. Here, we've added a colon and the word pair to the function parameter list, and an arrow symbol followed by the word int after the parameter list. These are annotations, and they associate the capital P pair type with the lowercase p pair parameter, and the integer type with the function's return value. These annotations don't do anything much while the program is running. They are stored as part of the function object and can be accessed, but they're otherwise ignored. Annotation values have to be written as valid Python expressions, but are otherwise unrestricted. Of course, If the annotation expression isn't something the type checker can recognize, type checking won't work. We've modified our even function similarly, except in this case, we're saying that the parameter named a is expected to be an integer, and the result is expected to be a Boolean value. We've also added a local variable called ret, and annotated it with the integer type, simply to demonstrate how variable annotations look. It still behaves exactly like the previous version. Now, let's take a look at our map function. The first parameter, named func, has always been expected to be a callable, which means a function or something that pretends to be a function. Now, we're marking it as such, using the callable type imported from the typing module. Callable has two type parameters, a list of the types expected for the actual function's parameters, and the type that the actual function will return. In this case, we're saying we want callables that accept a pair and produce an integer. The second parameter of the map function should be an iterable that produces pairs as we iterate over it. Finally, note that the return value from the function is an iterable that produces integers. Filter is not so different, except that its function parameter wants an integer as input and produces a Boolean value, and the second value should correspondingly be an iterable that produces integers. Okay, so all that work didn't fix anything about the program. It still works correctly with the correct input, and incorrectly with the incorrect input. No surprise there. Now we have this, though. MyPy is not built into Python, but we can download and install it using pipenv or plain old pip. When we run MyPy, it analyzes our whole program and points out places where we have, or more importantly could, violate our type declarations. In this case, there's a concrete violation, since we had code in the program to demonstrate the eventual exception the bad input would raise. However, instead of having to run the program and work out from the exception traceback where the bad data came from, MyPy is pointing to it directly for us, based on static analysis. If this really is faulty input, we're just about done. We can remove it, and the program will both pass the MyPy test and run without raising an exception. However, what if it's not bad input? What do we do if we want a list like this to be acceptable? Type checking doesn't mean that we have to give up on Python's flexibility. We just have to tell the type checker that we expect it to be flexible. To that end, we've imported a new generic type from the typing module, union. Union works more or less like an OR expression. Annotating a variable with the union of two types means that the variable is allowed to contain a data value of either type. Union isn't limited to two types either. We could use the union of 47 types if we needed to, although actually seeing that in practice would make me think the code probably could be simplified. Here, we've used union to create a new definition for pair, and to create a definition for a new type called single. A single is simply either an integer or a string, while a pair is either a two-tuple of integers or a two-tuple of strings. Using these new types, we've updated the annotations for our functions to accept integers or strings according to the type checker. We also need a new definition for the even function, since its parameter might be an integer, or it might be a string. The type checker can't catch the error if we forget to do that, but it did make us change the parameter type from int to single. Hopefully that acted as a flag to us that we need to make sure our code actually processes all the valid values of the single type. Now, MyPy is happy, and both the pipes run through without errors, because in the process of making the inputs acceptable to MyPy, we noticed and fixed the limitation in the even function. That brings us to the end of this video.